Welcome to MarinEngBase. In today's video, I'm going to review you about static excitation system. And in my previous video, we have discussed about the error-operated AVR. And this kind of AVR, the static excitation, is pretty much interesting because it is much more faster than the error-operated AVR. Usually, if you say it's about 10 times faster than the error-operated AVR. So we'll move to identify the basic components of this static excitation as well as what is the function behind it. In this diagram, that I have shown a very basic or simple construction of static excitation system. In the left-hand side, you can see your alternator, the stator winding, and the rotor. The rotor consists of the main field excitation winding, and it is connected to this set of slipping rings. And this field winding is excited by a three-phase rectifier bridge, which is connected to a special device we call a compound transformer. And it is secondary is connected to the rectifier bridge. And the compound transformer, it has three sets of winding: primary 1, primary 2, and the secondary. The primary one is having much more number of turns than the secondary and the least number of turns with primary 2 winding. And the other specialty of this compound transformer, the way how it connected. The primary one is connected in parallel to the stator output, or we can say it used as in shunt configuration. So it is connected shunt to the main stator output. Whilst your PR2 winding, and it is connected in series to the stator output. So the secondary is subject to both the magnetic field flux created from PR1 winding and PR2 winding. As the PR1 winding is connected parallel, mainly because of the voltage of the stator output, it will produce the magnetic flux. So we can represent this flux is mainly created because of the generator voltage. Whilst your primary 2 winding is connected in series, so whenever there is current flow, at that time the PR2 winding produces magnetic field. So we can see this magnetic field is created because of the current flow. Right, let's see how that basic operation takes place. Let's start the generator. So once you start the generator, as your main field winding starts spinning, and due to the residual magnetism, the stator wheel starts to produce some voltage. And we notice here that your air circuit breaker is still not connected. And it is open load condition, which means from the busbar side, there is no load connected to your stator winding, hence no considerable amount of current flow through the PR2 winding. But as this PR1 winding is connected in parallel to the busbar, it creates a closed circuit path where there will be a small amount of current flows through this circuit. And because of that small current, the PR1 will start to produce the magnetic field, which acts on your secondary winding, and the secondary winding will produce an EMF, which then will rectify to make it easy and connected or supplied to your main field winding. So the main field winding, the magnetic field strength will increase, and the stator output will be come up to the rated band. And the winding ratio of this primary winding and the secondary windings are matched in such a way to give the no load voltage of the stator or the alternator, and same time the PR2 ratio is decided or designed in such a way when your alternator or the generator connected to the bus bar and the rated load or the maximum load that the generator will maintain its rated voltage. So the PR2 winding and the secondary, as well as PR1 winding and the secondary winding, so the turn ratios are matching such way. So at the beginning, actually, the PR2 will not involve much with the flux generation because the current is small as the ACB is not close and the busbar is not drawing much current. So in that case, the primary one winding will the mainly creating your flux and the one responsible to maintain your rated voltage and the stator output. And as this PR1 winding is responsible with the or response to the voltage, that we can say the current which flows across this PR1 winding is mainly because of the voltage of the stator. In that case, the voltage and the primary one current will follow the same phase because only connected load to this transformer part is your main field winding and the rectifier bridge. And its impedance value is very much small and the power factor is it's almost unity. So which means more or less like a resistive load. So that we can say theoretically this voltage and current will be in the same phase with respect to the applied stator output. If you ever think why we call it as static excitation, the reason is the only rotating element is your main field winding. There is no part of the excitation system takes place in this rotary mechanism. So basically your excitation part is stationary, so we call it as static excitation. In this particular arrangement of the diagram, the system, we have used two sets of clip rings to feed your main field wind. Let's see now what happens once that your circuit breaker closed and the bus bar is connected with the alternator. Here, I have updated the diagram with two another sets of components. One set of reactor coil and one set of capacitors. The purpose of these two are yet to be revealed in later part of the video. Okay, now still your alternator is rotating. Let's say that it's produced an EMF because of the residual magnetism and that output voltage is shunt connected to the primary winding and it produces a magnetic field and that cuts the secondary winding because of that and EMF induced on the secondary winding which produces an alternating current and that alternating current starts to flow through this diode bridge and where the slip ring it will feed your main rotor and to maintain the no load voltage. Now, in previous case, without reactor coil, that we have seen the current through the primary winding. One was in the same phase as the stator output. But by adding this reactor coil, what will happen? In theoretically, the current will lag 90 degrees behind the voltage of the stator output. And there is a specific purpose to add this specific component. And if you see the vector diagram that we can see, the new current which is pass through the primary one winding will be 90-degree lag your initial voltage of the stator voltage because of this action of the reactor coil. So now we can see the primary one current is 90-degree lagging the voltage, and it serves a specific purpose. Now we connect the ACB and then a load to the stator. As the circuit breaker is closed, the load is connected to the generator. There will be considerable amount of current. It starts to flow through the R2 winding and it starts to produce a magnetic field. Then the secondary winding of compound transformer will be subjected to two magnetic field effect from PR1 as well as PR2. As PR1 is connected shunt with the stator output, its magnetic field because of the voltage mainly produced, whilst PR2 magnetic field is mainly produced because of the load current taking from the stator. Whenever more loads are added to the bus bar, the current amount which draws from the stator will be higher. In that case, the magnetic field strength of the PR2 winding will increases and this induced EMF on secondary will be increases, creating more flux to produce in your main field winding and compensate required amount of excitation to maintain the generator output at rated voltage. As there are two magnetic fields in action, especially act on the secondary winding, and each other crossing, these two should not diminishing each other's magnetic field strength. To eliminate such diminishing effect between these two magnetic fields, that we are using a set of reactor coil in series to the PR1 winding. Then the current flow through the PR1 winding will lag 90 degrees the generator output voltage, whilst the current flow through your PR2 winding will be at an angle of the power factor of the bus bar. Then the resultant magnetic field effect will be in such direction represented by this I resultant arrow in this vector diagram, and which is designed in the designing stage to achieve the maximum effective angle to produce an EMF on the secondary winding. So the use of this reactor coil is only necessary when the generator is connected to the bus bar, because only that time that PR2 will start its magnetic field. When the load is not connected to the stator winding, your PR2 winding will not produce magnetic field and there will not be any diminishing effect. So at that time, this reactor coil will not serve any purpose. So if we keep engaged this reactor coil at all times, what happens? It adds additional impedance value, like resistance, to this PR1 circuit. Then there will not be sufficient amount of current flow through the PR1 winding, and thus the generator or the stator output voltage will not be maintained at rated value whilst there is no load, or the generator will fail to maintain its rated voltage at no load situation. What we can do to eliminate that, at no load, we have to remove the reactor coil. physically it is impossible or impracticable. So what can we do? We can use set of capacitor coil which can keep in resonance with the reactor coil, so that it will eliminate the impedance value of the reactor coil. So this capacitor coil and the reactor coils are designed in such way at no load RPM, which is normally slightly higher than the loaded RPM. At that RPM, this reactor coil or capacitor will get into synchronism, and it will eliminate that impedance value. It's like that physically you remove the reactor coil and directly connect this PR1 winding across the shunt winding in my previous simple sketch. So that is the reason behind that we use a set of capacitor here. First, it serves the purpose that it will remove the reactor coil at no load. And the secondly, let's say when the generator is running and it's driving a load, if there is a temperature rise in this rotor winding or the main field winding, as well as the rectifier circuit or the secondary circuit, due to that elevated temperature effect, the impedance value may increase of the secondary circuit and reduce the voltage or the current, and then the main field strength will be lower. At such situation, your capacitors will provide leading VAR, and then it will maintain your rated voltage by providing additional current or voltage required to maintain the stator output voltage. So the capacitor serves two main purposes. One is resonance with the reactor coil at no load. The other one to compensate any voltage drop in the secondary winding, especially in the main field winding due to temperature effect. Let's see why this system is much more faster than the error-operated AVR. In this configuration, as the loads are drawing the current from the stator, at the same time, the current through the primary two winding increases and enhances its magnetic field. In return, it will increase or enhance the magnetic field of the rotor instantaneously. So as the loads are getting more, the current getting higher, and at the same time, the magnetic field will get automatically corrected to produce the rated voltage. So actually, PR2 is responsible to provide mainly the load time excitation, whilst PR1 is responsible to provide no load excitation. I hope you understand the basic operation of the static excitation system. On next slide, I'm going to show you the real component arrangement of such AVR. In modern days, this AVR system, excitation system, is combined with error-operated AVR system to enable the group sharing or the sharing facility. Because this kind of excitation system, for arranging its group is quite difficult. So that we can overcome this by introducing error-operated AVR system into the static excitation system. On this slide, I have shown two sketches. One, this sketch is the one which we have familiarized, and the other one is the actual arrangement of the static excitation system, which is mounted in the alternator. This is your PR2 winding, which is connected in series. This is your stator output, and that is connected in series with the stator output. This one is your PR1 winding, which is connected shunt, and actually this secondary and PR1 is together around here, and this is the combination of this PR1 and secondary. This reactor set of coil. This inner set of coils are the reactor set of coil and the capacitor band that you can see here. So the other components with detailed description, how and error-operated AVR incorporated into this system. Why is even in these brushes and how we can make it as brushless, plus the load sharing arrangement of this AVR. Modern, we can say it is a functional AVR, or we can say it is static excitation or static AVR. So on next video, I'm going to explain you about all these with a practical application. In modern day practical generator system is kind of this arrangement. This is your alternator, stator, rotor, and excitation windings, brushless excitation system. You have current transformer connected in series and potential transformer connected in parallel. And let's say your excitation system, static excitation system is this. And your operator system is separately feed. And from both of them, that the excitation is corrected through rectifier or the SCR system. And then the generator output voltage is maintained whilst load sharing function also enabled. So regarding this mechanism and with the actual components, let's discuss on next video. Thank you for being with me and stay tuned to update with new electrical, mechanical, hydraulic and pneumatics technologies and engineering concepts. Please subscribe still if you are not subscribed.